Hello everyone, welcome to my YouTube channel SG Chemistry Lectures. So in today's video, let us try to understand about photochemistry and its related terms. So first let us see what is photochemistry. So from the name itself it is very clear. Photo is something related to light and chemistry you already know. So here photochemistry is again a branch of chemistry, or I can say a branch of science in general, which deals with the chemical reactions which is caused by the absorption of radiations in the wavelengths especially lying in the visible and the ultraviolet region. And these reactions, the study of these reactions is called as the photochemical reactions, and that is what we are going to study in photochemistry. Okay, so here you can see in this picture, so here the molecule when it is in the ground state and then it absorbs energy. Here we are talking about energy, especially the light energy, because we are studying about photochemistry. So when it absorbs light energy, the molecule goes to the excited state and then the products are formed. So this is the general picture of what is going to happen in photochemistry. So let us try to understand more concepts. So before that, before going into the detail, let us try to understand what is the difference between photophysical process and photochemical process. So both are related with light, right? So photophysical and photochemical. So what is the difference between these two? So photophysical process, these are the processes in which the substance will absorb light but it does not undergo any chemical change. But here in photochemical process, again, since both are related with photo, that means both are related with light, but here in photochemical process, the substance here in this process, what happens, there is absorption of light and the chemical change also takes place. Here example, we can give the very simple example where combination of hydrogen and chlorine takes place to form HCl. So next, photophysical processes, what are they, what are the different types and how it happens? Let us try to understand. So here you can see that when the light is absorbed, the electrons will jump to the higher orbits because of absorption of light, or sometimes if the energy absorbed is very high, the electrons may leave the atom also. Okay, so photophysical processes are of three types based on the amount of energy absorbed by the electrons as well as the nature. So first case is, as I've already explained, the electrons jump to the higher orbits or they can also leave the atom completely. The next case is where the absorbed light is emitted immediately or instantaneously, and this process is called as fluorescence. The next case, that is a third type, is where the absorbed light is emitted after a particular time lag. So this process is called as phosphorescence. So this is about photophysical process. So you can just see a picture here to understand what is meant by photophysical process. So here you can see there are different states. About the singlet states, triplet states, we will be talking a little bit later. So before that, let us just see here. Here you can see the excitation, which is marked in blue, and then again the as I've already told, the energy will be absorbed, and then if it is emitted immediately, then you can see the green colored, which is representing the fluorescence effect, and you can see something which is marked in red where there is a time gap, and you can see there is a change in the states. You can see that from S1 it is going to T1. So let us see about what is S and T, which is nothing but singlet and triplet state. So you'll be learning about it a bit later, but now you can see how the phosphorescence has been marked. So this is about the photophysical processes. Now let us try to understand how these photochemical reactions are different from thermal reactions. So we know that in chemistry we have so many different reactions in which the heat is absorbed and the products are formed. So here we are talking about thermal reactions, right? So we should know how these photochemical reactions are different from the thermal reactions. So when I'm talking about photochemical reactions, again very simple, light is very much required here, because here these reactions occur by the absorption of photons of light, whereas thermal reactions, as the name indicates, here there is absorption of heat. So evolution or absorption of heat takes place during these reactions. In photochemical reactions, light is compulsory, it is required, whereas thermal reactions, they do not require any light. It's not very compulsory, or it's not necessary, I can say. In photochemical reactions, the temperature does not play an important role, whereas in thermal reactions, temperature plays a very important role. Here in photochemical reactions, the energy that is required for the reaction is gained by the absorption of light, whereas in thermal reactions, the energy is gained by the intermolecular collisions. In case of photochemical reactions, only a single selected species can be promoted to the higher energy level. So there is a selectivity here, whereas in thermal reactions, there is no selectivity as such, because there will be so many molecules which will absorb energy together because of the heat, and then the products may be formed. So you cannot gain selectivity in this case of thermal reactions. Now let us try to understand more about photochemistry. So before that, we should learn about the laws of photochemistry. So there are two important laws which governs the pattern with which the reactions takes place under the because of the absorption of light. So first one, let us try to understand Grotthuss-Draper principle on photochemical activation. So here, very simple. So when light falls on the object, a part of it is reflected and a part of it is transmitted, and only the rest of it is absorbed. So we are talking about the reactions that are taking place in the presence of light. So this reaction or the chemical change what we are talking about, it is only because of the light that is absorbed by the reacting system, whereas the remaining light will be reflected as well as transmitted. Let us go to the next law, that is Stark-Einstein's law of photochemical equivalence. So here, what does it state? In a primary photochemical process, each molecule is activated by the absorption of one quantum of radiation. So you can see in this picture, so there is a reactant molecule, it is absorbing one photon, okay, and then you can see it goes to the excited state. So excited molecule you can see in the second picture, and then of course the product will be formed because of the absorbed light energy. Now let us try to understand what is quantum efficiency. So quantum efficiency is given by these different mathematical expressions. So it's very simple. So here you can see in the first one, number of molecules that react divided by number of quanta of radiation absorbed. So this we have seen just in the previous slide, right? So each molecule will absorb one quantum of radiation and then it forms a product. So how many molecules will absorb how many quantum of radiation? Based on that you can calculate the quantum efficiency. Next formula, number of moles that react divided by number of Einsteins of radiation absorbed. So 1 mole of a substance absorbs 1 Einstein of radiation. So you can just calculate how many moles will absorb how many Einsteins. So based on that you can calculate the quantum efficiency. The next one is number of moles of product formed divided by number of Einsteins of radiation absorbed. So you can also use this formula to calculate the quantum efficiency. So now let us try to understand about what is a primary process and what is a secondary process in photochemical reactions. You might have seen in the second law, right? So it states that in a primary process, so that is what we are going to study now. What is primary process and what is secondary process in case of photochemical reactions? So primary process is where the light radiation is absorbed by an atom or a molecule, and here the atom or the molecule goes to the excited state. Okay, so this is the primary process. Now, what happens in the secondary process? There are various ways with which, or there are various ways in which this molecule can change itself. Okay, so first one, there is the condition. There are various results what may happen because of the primary process. The first condition, or the first we can say the first result that may take place is that the excited molecule may undergo one of the following changes. So what are the different changes? So first way is it can react to form the final product. So that is one possibility. Next is it can partly or fully deactivate itself and there is no reaction that is occurring, so there is no product that is formed at all. And the third possibility is that it can start a chain reaction. So in the first case, just the product is formed. In the second case, there is no product at all because it is deactivated. In the third case, so many products, so many molecules are formed because of the chain reactions. So these all come under secondary process. Now, let us try to understand a little more detail about this secondary photochemical processes. Let us take an example of hydrogen-chlorine reaction. So when a mixture of hydrogen and chlorine is exposed to visible or UV light of wavelength less than 480 nanometer, so a fast reaction takes place. So here you can see the formation of hydrogen chloride takes place. Here the quantum yield is very high, exceptionally high, that is to the range of 10 to the power of 4 to 10 to the power of 6. So you can see here in this case, since just by looking at it, it is very clear that quantum yield is too high. That means so many molecules of the products are formed. So you can easily understand that a chain reaction has taken place. So in the secondary process, a chain reaction has been taken place, because of which there are so many molecules that are formed. So quantum yield is too high here. So what actually happens? What is the mechanism? So chlorine in the presence of light, so you can see the reactions. The first reaction, chlorine in the presence of light, it forms two chlorine radicals. Free radicals are formed. So this is the initiation of the chain. Now this radicals will react with hydrogen, because we know that hydrogen and chlorine react, right, to form HCl. So this chlorine radical will react with H2 to form hydrogen chloride, HCl, as well as again the radical of hydrogen is formed. Now again this radical will react, the hydrogen radical will react with chlorine molecule. Again you can see there are chlorine radicals that are formed, Cl radicals. Now finally these steps, they go on repeating, so that's why we call them as chain propagation steps, because these steps will go on repeating itself. Finally the reaction has to come to an end, right? So how does it come to an end? The free radicals will come together. So chlorine, you can see two chloride free radicals, they come together, chlorine free radicals, they come together to form Cl2. So on the walls they combine together to form Cl2, and of course this step is called as the chain termination. So here the HCl formation stops, the HCl formation stops, and of course the chain, whatever the chain reactions were taking place, that comes to an end here. So now coming on to the next topic, that is photosensitization. So what is this sensitization? So from this term itself it is very clear, sensitization. So when the reactants, when they can't combine together as such in the presence of light, then you add something so that the reactants combine in the presence of light to form the product. So this is as simple as that. That is called as the photosensitization. So foreign substance which when added to a reaction mixture helps to start the photochemical reaction without undergoing any chemical change. So here the foreign substance, it does not undergo any change. So you are adding this substance so that the reactants combine together in the presence of light to form the product. So this is called as the photosensitization, and this foreign substance what you are adding is called as the photosensitizer. Now let us take an example and understand this in detail. So hydrogen molecule by itself, if you take only H2, by itself it cannot absorb radiation of wavelength 2537 angstrom. So now what happens when mercury vapor is added, when it is mixed with hydrogen, and then now here mercury acts as a photosensitizer. Okay, so what happens here? Mercury in the presence of light, the mercury it converts into the excited state, Hg star, that is in the excited state. Now this Hg star combines with H2 hydrogen to form two hydrogen atoms. Okay, so this is what happens. So this is how the dissociation of hydrogen takes place in the presence of light. So now photochemical equilibrium, let us try to understand this. So equilibrium, from the name itself it is very clear. So we have studied about chemical equilibrium, where the rate of forward reaction is equal to the rate of backward reaction. So all these things we are already familiar with. So what is photochemical equilibrium? So how the photochemical reactions come in equilibrium? So under what conditions these take place? So here in certain cases, a photochemical reaction is followed by another photochemical or thermal reaction in the backward direction. So the rate of photochemical reaction is proportional to the intensity of the light radiation that is absorbed, and it is also, when we are talking about the reverse reaction, the rate of thermal reaction, it is directly proportional to the concentration of the photochemical product. So once the product is formed, if the reverse reaction is possible in under thermal conditions, so let us say a reverse reaction is thermal in nature, then the rate of the backward reaction is dependent on the concentration of the products that are formed, the concentration of the photochemical product that is formed. So for the state of equilibrium, we know that the rate of forward reaction has to be equal to the rate of backward reaction. So you can see in this simple reaction here, both the forward and backward reactions are in the presence of light itself, photochemical reactions itself. So when the state of equilibrium is reached, the absorption of light will not take place further. And even if it takes place, there is no chemical change, because once the products are formed, the products again they react back to give the reactants. So this is what happens when equilibrium is reached. So at this stage, the reaction is said to have attained photochemical or photostationary equilibrium. So you can see in this picture, both the forward and the backward reactions, the rate of forward and backward reactions are equal here, and both of them are photochemical reactions, and of course here the equilibrium is observed. So now let us try to understand singlet and triplet states. So here, very simple, you can see this picture. If you just remember this picture, it is very simple to understand what is singlet and triplet states. So when all the spins are paired up in the ground state and there is no net magnetic moment due to the opposite spins, then we call it as singlets. These are non-magnetic states. Okay, you can see in the first picture, singlet ground state. See, there are the two spins, they are opposite to each other. So the magnetic moment, the net magnetic moment is 0. In the second one also you can see the singlet excited state, when one of the electron jumps to the higher energy level, but you can see the spins are opposite. So since the spins are opposite, the overall magnetic moment is 0. But what about the triplet state? So here, when one of the electron spins is inverted, then the new state formed has two unpaired electrons. So you can see in this case, in the third picture, you can see triplet excited state. Both of them have similar spins, the same side. They are not opposite to each other. So you can see that there is net magnetic moment, right? So this is called as the triplet state. So singlet state has 0 magnetic moment, and triplet state has net magnetic moment. Now in Jablonski diagram, I think it makes more sense now. So here you can see in the first case, which is marked in green, so here there is excitation of electrons. So you can see from S0 it goes to S1, or some electrons can go to S2, or we can also talk about molecules which undergo excitation here. So this is about absorption. So absorption of radiation takes place in the presence of light. Now internal conversion means here the molecules which are in the excited state, they can fall back from S2 to S1, okay, or from even in S1 you can see there are sub levels. So from these sub levels they can come back to the lower energy levels. So this is called as internal conversion. Now we can see that in the second case there is fluorescence. So we know that when the light absorbed is emitted immediately or instantaneously, then we call that process as fluorescence. Right. So we can see here from the S1 state, that is the S1 and S0, both are singlet states, but S1 has higher energy level. So from S1 state, when the molecules come back to the S0 state, this is called as fluorescence. Now there is phosphorescence, what we are talking about. So here there is intersystem crossing. So from the S1 state, the molecules can go to the T1 state, that is the triplet state. So after that, after they go to the triplet state, they come back slowly, that is they come back to the S0 state, that is the ground state. Slowly means it's not too slow, okay, but compared to fluorescence it is slower. So this is called as phosphorescence. Now let us try to understand fluorescence and phosphorescence in detail. So fluorescence, we already know, it is instantaneous emission of radiation by an excited atom or molecule, that is called as fluorescence, and the substances which absorb radiation and then immediately re-emit the energy are called as fluorescent substances. The phenomenon of delayed fluorescence is phosphorescence, which we are talking about, and these substances are called as phosphorescent substances. Let us look into the differences between fluorescence and phosphorescence. In case of fluorescence, the emission of radiation is rapid. So here the time range is so fast, that is 10 to the power of -3 to 10 to the power of -8 seconds. So fast the re-emission of the radiation takes place. Whereas in phosphorescence, emission of radiation takes place slowly, almost the time range of 10 to the power of -4 to 100 seconds. Next, in fluorescence, the radiation emitted is mainly because of the transition between S1 and S0, whereas in case of phosphorescence, it is between T1 and S0. Fluorescence stops as soon as the external light is removed, whereas phosphorescence is observed for some time even after the light is removed. Next, talking about chemiluminescence and bioluminescence. So these are again two terms related with that of what we are studying about reactions in the presence of light. So here, the phenomenon in which chemical reactions are accompanied by the emission of light. So along with chemical reactions, there is emission of light, that is called as chemiluminescence. So example, lucigenine is oxidized by alkaline hydrogen peroxide under mild conditions to give green chemiluminescence. So you can see that light is released, okay, the emission of light is taking place, not released, the emitted, I can say. So the emission of light is taking place along with the chemical reaction, that is chemiluminescence. Bioluminescence, very simple, bio is related to living organisms, what we are talking about. So the phenomenon of this chemiluminescence in living organisms, that is called as bioluminescence. Example, emission in fireflies. Next, talking about the Beer-Lambert's law, very important law in case of photochemistry. So first let us look into these two laws separately. Lambert's law, what does it state? When monochromatic light passes through a transparent medium, the rate of decrease in intensity with the thickness of the medium is proportional to the intensity of light. So whatever the light, the incident light, the intensity of light, how much ever you're going to increase, that is proportional with that of how much the rate of decrease, the intensity decrease, what it takes place, as well as the thickness of the medium. So all these are related with each other. Next is Beer's law. If the absorbing substance is present in the solution, the absorption of light depends upon the concentration of the solution also. So all these are interdependent. So both these laws can be combined together and it can be stated as such. The rate of decrease of intensity of radiation with the thickness of the absorbing solution. So you take a solution and you just put a light, okay, so that the solution absorbs light. So what happens once the light passes through this solution? Of course the intensity of the light decreases. So the rate of decrease of this intensity of radiation here, it depends upon the thickness of the absorbing solution. So what is the thickness of the solution what you are taking, so that the solution which is absorbing the radiation, and all these are proportional to the intensity of the incident radiation and also to the concentration of the solution. So what solution you are taking, whatever is absorbing the radiation, so you are going to look into the concentration of that solution as well. So we have a simple formula. So A is equal to log I naught by I is equal to epsilon ELC. So A is absorbance, I is intensity of incident light, I naught is intensity of transmitted light. So it of course it decreases, the intensity decreases because it passes through the medium. Epsilon is the molar extinction coefficient. L is the path length of the sample. So epsilon LC it is. So L is the path length of the sample, usually 1 centimeter. When we take it in cuvettes, it will be 1 centimeter. Next, C is the concentration of the solution in moles per liter. So molar extinction coefficient, what we are talking about, that is epsilon. So how do we define it? It is a specific absorption coefficient or absorbance for a concentration of 1 mole per dm cube and a path length of 1 centimeter. So that is the way we define this epsilon or the molar extinction coefficient. So this is about Beer-Lambert's law, which is very important when we talk about photochemistry, because here especially when we do the experiments with respect to this photochemistry, this particular law comes into picture there. Okay, so I hope the various concepts that were discussed in this video were very helpful to you, and I hope the various concepts were very much clear to you. And yes, we have studied about, in this particular video we have discussed about the laws which govern photochemistry, also differences between photochemical processes and thermal processes, photophysical and photochemical process, how they are different from each other. Beer-Lambert's law also we discussed in detail, and also about the fluorescence, phosphorescence, how they are different from each other. All these things we have discussed, along with the smaller concepts like chemiluminescence, fluorescence, bioluminescence, as well as photosensitization. So all these photochemical equilibrium, so all these things we have discussed in detail. So I hope it is helpful. So please do like, share and comment, and also please do comment which other topics would you like to learn in other upcoming videos. Thank you so much for watching and have a nice time.